Today, I introduce two products which I am developing, Picoruby and PRK Firmware. Picoruby is a Ruby interpreter for one-chip microcontrollers. PRK Firmware is a keyboard firmware framework in Picoruby. Firstly, I'd like to talk about PRK Firmware. But before that, as I'm not sure if you are familiar with the DIY keyboard, let me explain it a little. Regarding today's talk, I want to focus on a thing. It's the approach of software and hardware. 10 years ago, there was a kind of barrier between software and hardware. We couldn't easily make a print circuit board because it's an unfamiliar field for software programmers. However, the internet totally changed the circumstances. Nowadays, you can design an electric circuit even on a web browser and send the data to a PCB manufacturer. They accept small amounts of orders and even assemble it into an almost final product if you make a proper BOM, bill of materials, which is a list of parts. The internet and cloud services played an important role in this revolution of production. You are now a keyboard builder this way. There are many factors in DIY keyboard though. These are the main points in my humble opinion. Keycap is the face of a keyboard. It plays a dominant role in composing the appearance of your keyboard. Switch is the core element. We call DIY keyboard also mechanical keyboard because of it. Some of my friends became obsessed with lubricating switches. They ever have that feeling where they are not sure if they are awake or still dreaming. Layout is the essence of building a keyboard. This is the CRKBD, which is a very popular split-type keyboard. Thanks to the separation of left and right, you can type in a comfortable posture. The small number of switches is compensated by changing layered keymaps that are defined in the firmware. Lastly, firmware is what I'm talking about. You have to use one of the firmware when you build a keyboard. I list 3 of them here. QMK is the most famous one when it comes to keyboard firmware. It's written in C and you have to write C in order to define your keymap. KMK is a recent product and CircuitPython based one. PRK Firmware is an alternative modern firmware platform that I released this year. PRK Firmware has still few stars. I'd like you to support by clicking star on the PRK Firmware, please. Anyway, let's take a look at how can you use PRK Firmware. This is Gherkin, so-called 30% keyboard because it has 30 keys. You may be wondering if 30 is enough. I also don't think it's enough for daily work, but I can deal with a small thing to do. And it looks kawaii, right? Above all, this is perfect for an explanation because there are few keys and its keymap is compact enough to see. The keymap.rb of Gherkin is here. You initialize a keyboard class like this. Then you initialize GPIO pins so that they work according to the circuit design. Eventually, you're going to define keymaps. As the code shows, there are 3 layers, for example. You can multiply a key layout in this way. Now let's take a little bit closer look. Key codes with KC prefix are predefined ones. Other keys like ENT raise and SPC lower are user-defined mode keys. You can specify your mode key with define mode key method. ENT raise works as the enter key if you push the key and release it quickly. On the contrary, while you are holding the key, the whole keymap switches to raise layer that offers symbols like exclamation, @mark, and hash, etc. The point is that keymap.rb is a pure Ruby source. I know you still don't get why you should be glad to be able to write a keymap in Ruby. Don't worry, I'll mention it later. So let me finish showing you the basic usage of PRK firmware now. Now you have your keymap.rb in this way. Next, please download a released binary of PRK firmware from GitHub. You're gonna get a .uf2 file after unzipping it. Then, connect the USB cable to the microcontroller while pressing boot button on it. I will talk about also microcontroller later. Let me skip the details of it for now. Anyway, RPI-RP2 drive should be mounted on your computer. Drag and drop the UF2 file into the disk. Then, the drive will be remounted as PRK firmware. The last step is to drag and drop the keymap.rb, which you wrote just a while ago. Here comes the first highlight of the show. PRK firmware will automatically reload your keymap. You noticed one thing if you are a keyboard lover. Indeed, you no longer need to compile your keymap by yourself. PRK firmware compiles your keymap on a microcontroller on your behalf. The technical secret of the compilation in Picoruby is another topic I will talk on the second half of this slot. Back to the keymap.rb. Let me show you some demonstrations. This is a mesh keypad I'll use from now. Mesh means name card in Japanese. It's a very popular kit among keyboard newbies in Japan because easy to build. First demo is Fibonacci number. Now you are seeing my terminal. Mesh will put 1 when I push a key on it. The next figure should be 2, then 3, 5, 8, and it goes according to the Fibonacci rule. This is an example of how you can extend your keymap in Ruby. The implementation of the Fibonacci class is pretty simple. The first 2 numbers will be created in initialize method. The subsequent number will be returned every time you call take method. Then all you have to do is passing a proc object to define mod key method. That proc object will be called when you press the corresponding key. Picoruby runtime environment reminds you of Fibonacci object and is able to call take method repeatedly. Next example is a password generator. Another key on the mesh generates random 8 letters every time it's pressed. I skipped the details of the implementation, but note that whether the random string is strong enough as a password or not depends on the implementation and the quality of the pseudo-random number generator of the chip. Next is a more practical example, especially for Vim users. You generally configure in .vimrc file so that colon and semicolon are swapped. Because colon is one of the most frequent key in Vim, and you naturally want to type colon without shift modifier. It's really easy to do it because PRK firmware has invert shift method out of the box. You just write a condition that you want it to work in a before report filter, which is similar to before filters in Rails. The implementation of invert shift is also quite simple. I don't know if inverting control modifier is useful or not though. Let's see invert control method instead of invert shift this time. It's just an example of how to invert a modifier key before reporting key code. Modifier keys are represented in 8-bit data. The rightmost of bit represents the left control key, and the 5th bit represents the right control key. Once you understand this, the rest is easy. It's just a bit operation like this. The point is that these implementations can be written in keymap.rb file, and PRK firmware will compile it and reload it on the fly. The last demonstration is the Ruby mod key. Do you sometimes want to use Ruby while you are taking notes on the text editor, don't you? I do. My keyboard starts to blink red when I press the Ruby key. I'm very sorry I couldn't show the real blinking keyboard, but what is real? How do you define real? If you are talking about what you can write, what you can refactor, what you can run and see, then real is simply electrical signals interpreted by PRK firmware. Let's say, what if you want to know the result of 3 to the 7th power? My keyboard tells me. What is happening? The answer is Ruby. As you can see from the fact that the keyboard is able to dynamically compile keymap.rb, your keyboard has a Ruby interpreter. Or if I can say so, there is an IRB inside. As it is a kind of IRB, you can create a Ruby object. The keyboard remembers your object. It's almost a joke though. You can make an even class if you want. Of course, you can make an instance of the class and call a method. I think I can say kind of revolution. We are approaching the next main topic, Picoruby, but still one more thing I have to mention, the microcontroller. PRK firmware runs on an RP2040 chip assembled on Raspberry Pi Pico. Raspberry Pi Pico is priced at $4, which is very reasonable. It is not only cheap, but also good in functionality and performance. RP2040 has 264 kilobytes RAM and ARM32-bit Cortex-M0 Plus processor. On the photo, the whole of this green board is Raspberry Pi Pico. When I say RP2040, it indicates that little square chip on the center of this board. On top of that, because Raspberry Foundation distributes the RP2040 chip, other manufacturers can make boards like ProMicro. ProMicro is Arduino-compatible board and the most popular one in the DIY keyboard market. In fact, we can buy RP2040-based ProMicro. These are the reasons that I decided RP2040 is the target chip of PRK firmware. That's all about PRK firmware. We are going to dive into Picoruby, which is the programming language of PRK firmware. But before that, I want to talk about how the Ruby community helps us to make the ecosystem better. The Ruby Association in Japan is an NPO devoted to the advancement of the Ruby programming language. They give a grant program every year that offers financial help to develop projects related to Ruby implementations, libraries, and frameworks. My project, Picoruby, was fortunately chosen last year. What's more, Matt himself has been responsible for my mentorship during the project. I could, even now I still can, text him to ask how Ruby works, why did he design Ruby like that, and what are his opinions to make a better implementation. Our company also helped me. They allowed me to develop Picoruby during business hours. Thanks to those big supports, I successfully submitted the final report. Anyone, including you, can apply for the Ruby Association grant. Since this year's taking application has ended, I encourage you to apply next year. Okay, let's go forward to Picoruby. I think it's a good starting point for an explanation of how does the Picoruby runtime work. Because Pico IRB that we've just seen is a good example of a runtime. It is a multitasking system that manages multiple tasks. Those tasks switch one after another at every 1 millisecond. This image shows transition patterns of the status of tasks. These orange boxes are tasks. Only the task can become running state at the same time. running task executes its VM code for 1 millisecond, then moves to the tail of the ready queue. There are multiple tasks in the queue, things like a task that scans what keys are pressed, and a task that blink LEDs, for example. This rotation is normal processing. Left side of this image shows other tasks. If a task internally calls lock method of a mutex object, and if it fails because probably another task already has exclusive rights, the state of the task will become waiting, and the task waits until the mutex is released. This task also in waiting queue because it called sleep method and will wake up after the time has passed. The task can also let itself suspended. This task stops until being resumed by another task. All the tasks described so far are infinite loops. An application for microcontrollers consists of multiple infinite loops. But if a task doesn't have infinite loop and execution of the task reaches the end of the script, the state of the task becomes dormant state, then the task will be freed to return memory to the system. The task of the Ruby mode of IRB I've just showed you is a kind of this task. However, I don't want it to be freed because I'll use the Ruby object again. So I made a special task that is named sandbox task. This kind of task is never freed and resurrected repeatedly. Well, it's time for Picoruby. It is an alternative mruby implementation for one-chip microcontrollers. The one-chip microcontroller is the motivation to develop Picoruby. In general, an mruby application consists of a VM code and a VM. Unlike CRuby, you are able to separate the whole process into compile and run. Due to this concept, RAM consumption of mruby-compiler is not so much small. Technically, you can embed also Ruby script and mruby-compiler if you have enough memory. mruby/c is a smaller virtual machine than mruby that also can execute mruby intermediate code on a one-chip microcontroller. Also, combining mruby/c and mruby-compiler spoils the feature of small footprint of mruby/c, so it doesn't make sense. That's why I'm developing the Picoruby compiler. Picoruby is a Ruby interpreter that integrates Picoruby compiler and mruby/c virtual machine. Because I have been an mruby/c committer from a few years ago, I could imagine how can I make them work together. It's easily imagined that there are some technical challenges to realize it. The syntax rule of Ruby is complicated. It's a reason that we can write Ruby as we wish and that we love Ruby though. Making a Ruby compiler that has small footprint takes time and effort. You might think that we have a bigger microcontroller like ESP32. It may be able to make mruby and mruby-compiler work together. But we can't always use such a rich microcontroller. The bigger RAM, the bigger electric energy consumption. Trying to make a smaller compiler is meaningful even in the future. Actually, the existing mruby compiler depends on the mruby itself. I guess this is the most only reason for big footprint. Depending on mruby means you can use useful mruby objects like array in the compilation process. On the contrary, I need to make each fine logic minimal in the Picoruby compiler. To make it small, I use Lemon as the parser generator instead of Bison. Bison is the most popular parser generator which is used in both CRuby and mruby. Lemon is originally the parser generator of SQLite. One day, I asked Matt how to make a Ruby compiler for microcontrollers. He told me that Lemon seems to be able to generate a small code. That's why I'm using it. But to be honest, I still don't know if Lemon is really helpful to make a small compiler or not because I didn't make a detailed comparison with Python. Anyway, it's true that the Lemon-based parser is small enough and works well so far. Small code basically means ROM consumption is small. ROM is also important though. My biggest point is RAM. I explain how I'm making the RAM consumption of a Picoruby compiler small from now. Let's take a look at how it is actually small. This command is how I measure RAM consumption. Valgrind is a troupe of memory debugging tools. We use Massif, which is one of the tools of Valgrind. --stacks option instructs Massif to survey stack memory usage in addition to heap memory. The rest of the argument is just a compilation command of mruby-compiler or Picoruby compiler. These commands produce a massifout.file. msprint is another tool to see the result of massif.out. Put as hello world is the most written Ruby script, I guess. This is the massif of compiling Hello World by mruby-compiler. It consumes 133 kilobytes. Here comes Picoruby compiler. It consumes only 17 KB and it's 73% smaller than mruby compiler. The next target is keymap.rb of mesh keypad. Sorry, but the letters are too small to see. Please imagine that this Ruby script contains initializing keyboard class, initializing GPIO pins, implementation of the Fibonacci class and the password class, which I mentioned earlier, keymap for 4 keys, and some define mod key methods. mruby-compiler compiles that keymap.rb with 206 KB. Picoruby compiler can do with 62 KB. It's 70% smaller. This is the secret that PRK Firmware can compile your keymap on the fly. I have to add one thing. These figures are measured in 64-bit Linux, so all the figures should be smaller when you exactly experiment on a 32-bit microcontroller. Anyway, you will be able to use about 220 KB for Ruby runtime from 264 KB, which is RP2040's RAM. But more than 100 KB is already allocated basically to make keyboard work. mruby-compiler obviously cannot compile mruby.rb within the rest of memory. Finally, I'll tell you what I did to make Picoruby small. Today I pick up 3 things. Let's take an overview. Depending on only libc and less. Considering paddings and pooled allocation. Freeing heap memory in a loop instead of recursion. All these things are topic in C. I hope I could share the mood of implementing the compiler. As I said earlier, mruby compiler depends on mruby to reuse mruby's useful objects. On the other hand, Picoruby compiler depends on only the standard C library. More exactly, depends on the C library for microcontrollers. I feel you are wondering what is the difference. glibc is the most popular C library though. We have other C libraries like newlib. Newlib is an alternative C library intended for embedded systems. There are some differences. Newlib doesn't have the implementation of regular expression, for example. It has a header file of regular expression, but surprisingly, there's no implementation at all. So I made a small regular expression module for the tokenizer of Picoruby from scratch. The next is about padding and pooled allocation. Imagine that we have a struct for linked list. Let's say it has 2 members. Next is a pointer that points to the next item of the list. Value is 1 byte data. The size of this struct is 8 bytes, not 5 bytes, because of a rule that is called data structure alignment. 3 bytes of padding is inevitable in C99. As we are a small footprint seeker, we should take this kind of padding into consideration when we allocate numerous structs. If you have a linked list that contains 5 items, it consumes 40 bytes to store only 5 values of 8-bit data. You will naturally think, how can you more effectively use the memory? Pooled allocation is a technique of packing data effectively. A struct, which is designed as a pooled allocation, contains an array of data as a member. It also manages the size of data and index of current data position. Thus, the total count of data is expressed as the product of the size of each struct and the number of the struct. Pooled allocation can reduce paddings, pointers, and memory fragmentation. Freeing in loop. One day, I noticed one thing while I'm looking at the massif. It has a spike at the rightmost of the mountain. I came up with an idea that can shave the peak. As a result of this attempt and some other ideas, RAM consumption was reduced from 53 KB to 24 KB on a benchmark code. What I did here is freeing in loop instead of recursion. When you delete a long linked list at once, call stack will be spiked up because nothing is deleted until the recursive call reaches at the bottom of the list. The code over recursion is beautiful, though freeing a list in a single loop doesn't make a stack spike. By accumulating small ideas like these, Picoruby is finally working on one-chip microcontrollers. That's it. I told you almost all about Picoruby and PRK Firmware. I will close my talk by touching on the significance of my projects. As Morpheus says, we are living in a world where the Micon is everywhere. Everything is connecting to a network. The importance of learning co-design between hardware and software must increase. Just like PCB manufacturers approached cloud internet, we software programmers should approach hardware. Picoruby proves that you can write a Ruby application for one-chip microcontrollers. PRK Firmware realizes the compilation of your keymap.rb on the fly. This means you can quickly develop an IoT system with Ruby. Ruby has just started its history of hardware programming. As is well known, Ruby became famous for the revolutionary concept of Ruby on Rails. So likening the microcontroller board to Rails, I entitled this talk, On a Keyboard, Ruby on Board.